the stream. So this is part three. Basically, it's a continuation of where I left off just now. So what I'm trying to do is I'm trying to get like a neural network to approximate a certain function, okay, which I think is not exactly the kind of functions that a neural network is typically decoding. Okay, but it is very similar to like those kind of polynomial regression with interaction variables, that kind of stuff. So this simulates that. Okay, but yeah. So based on what has been done so far, like we have come up with some like rough scheme to decode using a few variables, and then we just let the neural network try to solve it. So like with a variable 6, you can get all these things inside. You know what? Let's just for simplicity, let's just put the shift value as like a constant, and then like basically you just want to see whether just this function alone without the s can it already do it. So let's make the problem a little simpler. Let the network solve it. The network will be given the length of the message one hot encoding to the alphabet, as well as the shift parameter, which in this case is constant. Okay, we're just gonna check whether this can learn. Let's just use 5 epochs and see whether it works. So yeah, I made my shift parameter the same now, so it should be easier for the network to learn, and let's see whether it learns anything. So yeah, you see it's actually learning pretty well. The dense one, the basically the last node has already mastered the input. Okay, and now we can see that actually there's more learning done, you see. Okay, we have one other thing that mastered the input as well. That's dense 30, which is the second character. The third one still needs some time. Okay, all in all, it isn't that bad. Okay, the last digit and the second digit, so the second and the fourth character has an accuracy of near 1, while the first and the third has an accuracy of around 0.3, which is not too bad. So you can see that if let's say my shift value is like 1, you can see ZBZA, the oh the the last, oh okay, looks like shift, how's my shift value? My shift value was 1, yeah, was shift value of 1. Oh, interesting. I thought that okay, so it still didn't really work out that well. Okay, so that was if we were to fix the model's shift parameter. But let's go back to the original thing. So apparently this second one and this last one can learn if we fix the shift as a constant. I mean, it's just going to output itself, right? And okay, not itself, x0. And then what we can see over here is that they actually have some interaction between the terms here. So yeah, let's see whether this can work. For maybe we just go back to an arbitrary shift value. I mean, to make things easier, maybe we do like a shift value of 10. Yeah, so there's fewer possibilities to learn, I guess. So with 10, let's see how it learns. So just now with one shift value, the at least this dense 36 was able to learn. Okay, but it looks like if I just have a few different parameters, okay, it seems that it fails to learn. Okay, it seems like there's some form of interference that kind of prevents it from learning. Okay, so we kind of want to solve this. Yeah, just need to imbue the network with more stuff. So the first thing that I'm going to try is just to use a very basic architecture that is used quite often. It's like some like skip connections. Okay, so we're just going to make the network a bit more Okay, first up, before we use skip connection, let us see, okay, whether we could just increase the scale of our network, and then it perhaps could learn better. Okay, so let's just try it. I'm just going to increase the number of layers in the network. I'm increasing it to 3 layers of 1024 nodes, and we see whether this works. So let's take a look. So as usual, the last one kind of works. Okay, but this and this here, it doesn't really work that well. Okay, it's not exactly working very well. You can see that it is still stuck at like a 0.05, which is 5% accuracy, which is just a little higher than chance levels. Okay, it's increasing a bit, there's some improvement. Okay, so a deeper network may actually help. Okay, so it's actually increasing a bit of for the loss over here. Okay, let's push the limits a bit. Let's just do 10 layers of this. Okay, so we do have 10 layers now. We do have 10 layers of this dense layers that was initialized using this for loop here. And let's see whether this kind of works in making the model work well. I don't think it works. You see, in fact, actually, it kind of worsened the accuracy here. It couldn't learn this one already. Like, this part couldn't learn already. Originally, it could learn, but now it can't. Yeah, I don't think this is the right approach to do it. Okay, so you can see that if we just arbitrarily like make the network deeper, okay, it may not work out that well. Okay, how about this? Now we do what the skip connection thing does. Okay, so like for in range 5, okay, we can firstly do this previous equals to x. Okay, then we do a dense. Okay, then what we can do is we can do like a dense, okay, plus x plus previous, like something like this. Yeah, we see whether we can just add the layers like that. I don't think you can, but let's see whether it works. Oh, it can, is it? Oh, you can. Yeah, you can. Yeah, so you can't do this. We have to use an add node, I believe. So we can do this, two of this, and then after that we can just do x equals to add. Okay, then we can add in x and previous like that. Okay, so my previous is this thing here. Oh, I know why. Okay, it's because I I can't just do this. I have to I have to do a dance first, a dance layer like that. Then we can do this. Then in fact I can even do like stuff like this. But let's just try using this first. Mm, okay, maybe we try this and see whether it works. So it is like a skip connection every 2 dance nodes. Yeah, let's see whether this kind of skip connection architecture kind of works for this problem. In fact, actually, I think I just made it worse. Oh, you see, the accuracy is indeed going up. Okay, so it looks like it's learning this one. The rest of it learns a little bit also. Learns a little more. There's more accuracy now. You can see with this skip connection. Yes, with just adding a skip connection, it helps a lot. Yeah, it kind of like how do I put it? It gives more avenues for the network to learn more complex relations because of the skip connections. It has learned a little bit more. It is still not doing that great, but you can see some improvement. Okay, so let's see whether we can scale this up even more. Okay, so this was range 5. Maybe if I just take away 1, will this help? So let's try. So now I just only do like 1 layer. We see whether it works. Oh, yeah, it's working. It's going up. The loss is going down also. You can see the losses. Okay, it's around 0.08. Not too bad. Okay, so now the challenge right now is to see whether we can scale this up to a very large model. Okay, that was 5. Okay, let's try like 20. Okay, let's just wait for this to run finish first, then we try. So the accuracy is getting better. It's like around 23%, 12%, 23%. So the ResNet looks like it's kind of able to approximate more for this. So let's try a range of 20 for this, and then we see whether it works. So this is a super deep network. Okay, a super deep network, but then I do a skip connection here, which could potentially help. Yeah, I could also concatenate. I mean, we could try that also. It is not as great as before. So normally what people do when they have super big networks like this is that they add like batch normalization to it. So perhaps we can try that because like maybe the network is now too deep. So perhaps we could add some batch normalization layers to help to make the network a little more versatile. So of course this network is just to see what traditional methods can do for us. Okay, I do have some idea of what I can do in the network. I haven't tested it out, so I'll be doing it live right now later. Okay, so it's not that great. Not that great, about 8%. So the deeper network has some limitation. Let us try to put in batch normalization, which helps to normalize the outputs within a certain range. So what we can do is we can add the batch normalization here. So we have a batch normalization like this, and then we run the model. So yeah, you can see that the batch normalization is helping it a little more. It's, I guess it's working more, although it seems to be like stuck here. Hmm. Yeah, it's not too bad. It's just not the great. Yeah, I don't think it will perform better actually. Yeah, so we are not exactly able to do that great in this problem here. Although the function is very well defined and neural network is supposed to do a great approximation to this, somehow when we do like some form of interaction breadcrumbs between the inputs, it kind of breaks down. So yeah, this probably isn't the domain for neural networks to shine right now in its current form. Only the last one works. So you see all this not that great. Some improvement though. Yeah. So I guess 20 maybe a bit too deep. Maybe we try 10 later. Okay, why not? Let's just try 10 layers now. 20, I think, is a little too much. It's not improving. The performance is not improving. Try 10. ResNet like architecture, 10 layers. Let's see how it works. So modern day deep learning, people are just trying to make bigger and bigger models. They add the parameters here. Like for BERT, it's like 540 million parameters. GPT-3, a few billion. Nowadays, the models are in billions to tera parameters, which is kind of insane. So yeah, it doesn't quite work out. In fact, it actually the performance became slightly worse after we had batch normalization. Like this two is not they are not learning anymore. Okay, let's see whether is it because I added my batch normalization too early. Maybe I need to add it after I do that addition here. So you can see that it is currently not performing that great. I don't think it's I think we have reached the limit of using ResNet for this problem. Yeah. I guess if I were to stick the uh, like the S parameter to be constant, maybe you can learn. Like maybe over here, if I take away the S over here, it could learn this relation better. But right now, even ResNet is not able to learn. I think it can't even learn the modulo to begin with. So maybe the issue is the modulo, not really the network. So let's see whether I can change this. Yeah, it's not doing that great. You see over here is it's about 5%. It's about 8%. Still around the same as just now. Yeah. Okay, maybe let's make the problem simpler. Let's just do it for one shift parameter. Okay, we just do it for one shift parameter. So maybe just do a random.run in one, which makes the shift 0 actually. Then we run the whole model again, and then we see whether with just one shift parameter can the network learn. Because now there's no extra conditioning variable, it should be able to learn better. I say should because I'm not sure. Let's take a look. So yeah, it does look like it's increasing. Let's see the limits that it can go to. Yeah, it's actually quite fascinating to watch this train. So this dense 198 is still not so this dense 198 corresponds to this parameter here. Okay, I guess it's not able to learn this equation yet. Okay, let's see. So you can learn the last one quite easily. The first two, it's learning a little bit. The third one is not great. Yeah, it doesn't look like it's increasing anymore already. It looks about the same as the previous accuracy. So I think this is about the limit. If we don't shift the S parameter, I don't think even a ResNet can learn this. Yeah. Okay, maybe there's issue with the batch normalization, which let's just remove the batch normalization and see how it goes. Okay, if we take away the batch normalization, will it be better? So let's take a look. Okay, it does look like it's training faster now without the batch normalization. Accuracy is going up, so maybe this will be better for this regression model without the batch normalization. Yeah, it kind of hurt the performance just now. Now it's about 0.23 already. Okay, yeah, it definitely worked better. See over here, it became like almost one already for this. So this second one, the dance to one two, refers to this function here. This one. So we managed to learn this pretty well. Okay, it looks like it's learning. Let's give it more time. Let's give it more time. Let it learn a bit more. Maybe you can achieve 100% accuracy on this. Because actually, theoretically, it is about like hard memorizing the input relation, and it could be done if we have enough samples. Which in this case, we do have quite a bit of samples, so I guess you could potentially learn the relation. Oh, it's learning, it's learning. Look, it's learning. It's going to reach one already. This one is also going to reach one. So that was for only uh, one shift variable. Okay, it looks like it's learning, which is the shift equals to 0. Oh, that's pretty good actually. Everything can learn. Okay, so that was with one, and I think one this model kind of nailed it. Yeah, this nailed it. It's a ResNet with 10 layers, or rather 11 layers. One, two, three, four, five, six, 7, 8, 9, 10, 11. Yeah, 11 layer ResNet. Nailed it. Oh, but you see the actual string here looks different. Oh, I know why. This one should be input string. Okay, somehow it doesn't. Oh, because the shift value needs to be 0. Yep, okay. Yep, so looks like it's a 100% accuracy. I mean, I give this, it will get nonsense input because it doesn't map. Very nice. I have no idea how this cipher gets deciphered actually. Like I said, undo your operation, which I'm not sure whether it's possible. But yeah, it looks like it's 100% accuracy with just one shift. So that's actually pretty good. Now let's up the difficulty. Okay, we do incremental and then we just increase the shift by one. Okay, so here. So now I have either shift of 0 or 1. Let's see whether our model can learn it. Good luck. So this is a ResNet like architecture for MLPs. Let's see whether it can learn the relation if there's two alternating branches. The results look pretty promising actually. It looks like it's learning. So we can see that actually this complicated thing, if we fix the shift parameter, the network actually can learn the function. The network actually approximated the function pretty well, yeah, which was quite amazing. Yeah, these two look like it's learning also. We can let it run for another 5 more epochs, and let's see whether it works. Okay, so it's about 30% and 23% accuracy for the first character and the third character. The second and the fourth are close to 1. Let's try again. So it looks like it's improving. Yeah, it does look like it's doing well actually. Its accuracy is increasing as well. Mm. So maybe if given enough time, this might actually learn the relation. Mm. Okay, let's run it one more time to see whether it can work. Then after we give it the full treatment of all 10, I think it's learning. See, it's learning already. It's learning already. Very good. It's learning how to handle the input. So this is about 88 and this is about 83. I'm just going to give it run for another 5 more epochs to just see whether we can get it to like 100%. This one is going to 100% already. This one too. So it looks like we don't really need batch normalization. If not, it might hurt the performance of the model. Mm. Yeah, it's learning. It's learning. It's actually learning pretty well. Interesting. It might actually hit 100%. Not too bad actually. Not too bad. It's like 95%, almost 100%. Almost there. Almost there. Very nice. I think if we let it run for one more time, it might hit. Oh, but you see, although the training is 95%, and here is like where is it? Here is 95%, but the validation loss is about 70 and 80%. Okay, let's just give it one last try. So it means that it fits very well to the training data, but it may not be able to generate the relevant output for the validation or the test data. And it's fitting it really well in the training data. It's fitting the curve as well as it can. Okay, but the validation accuracy is like about 74%. Not too bad, not too bad. It isn't the best, but it's not too bad already. So this is the performance of a baseline ResNet, which is actually honestly pretty good. So now what I'm gonna do is I'm gonna give it the full blow. Okay, I'm gonna give it the full blow of 26 epochs, and then we see what happens to it. Okay, let's analyze what happens to the network when we give it the full blow of 26 different shift parameters and see whether this kind of architecture can still work. Okay, not bad. 80. So if we look at over here, like NSTDET, see, is actually doing pretty well. Most of the time, it can get you the right result. Yeah, in fact, it's doing actually a remarkable job. Yeah, only some errors. Okay, which is not too bad actually, to be honest. Okay, so now let's give it the full treatment. Okay, we give it the full treatment of our entire scope of this problem. Okay, we give it the entire range of all potential shifts up to 26. Okay, let's see how the model performs. So this is the full 26 shifts. Okay, just now maybe it could still memorize a bit, but this one, if you use all 26 of it, you have to figure out the formula. If not, you will have problems to solve it. Yeah, if you don't figure out the formula, there's no way you can, because you need to incorporate the formula here, like that. And you also need to determine the modulo. I mean, yeah, Okay, so if we do the full blown 26, I don't think it's gonna learn very well. I mean, it's increasing. The accuracy is increasing. We can give it another 5 epochs to see how well it goes. Yeah, about 60%. The rest, like, okay, let's try again. Give it another shot. Okay, so you can see that the accuracy is about like going to 11% already for the training accuracy. Okay, then we see the validation set, how good it is. It is about 7%. 5, 4, 6, P6. So there's a bit of overfitting here. Like here's 11, but here's only 7%. It's about 13%, but here's only about 7. So over here rise to 17% already. Okay, but the validation is still at 8%. So it looks like the model is overly confident here. So it can reach until about 21%. But the validation loss just doesn't, the validation set is still at 8%, which means that it's not exactly learning the right relations. I guess this is quite a hard problem for the network to solve. Yeah, it's like only slightly better than random guessing. So this is a little tough for the model to learn. Okay, so now let's see whether we can improve the model a bit. Okay, so one way to improve it will be to try other things. So there's this thing called GALU. Okay, so GALU is a gated ReLU. Okay, so basically GALU does this where we have like there's a gate. No, this is a little different. No, it's a little different from what I gated linear units actually. Self-gated activation function. So that's what we'll be doing. So self-gated means we apply a sigmoid, okay, to the function itself. So actually the improvement is not much. If you ask me, yeah, for Sci-Fi 100 it does show some improvements. Okay, I cannot find what I was thinking of doing over here, but there's this thing called multiply uh, the ReLU function. Is it a gated ReLU? Yeah, something like this. You have a sigmoid here multiplied by the ReLU. Yeah, it's something like LSTM. Yeah, it's a gate. Why it is better, I still don't know. Yeah, this one actually I have some inkling of why it works better because it's able to, especially when there's different kinds of functions like this in this context, when you have like different S that can influence it. Sometimes you want to not have a certain flow through a certain S. So the S can do the gating for the function. So we can let the S parameter gate it, okay? But then basically based on the gates, your activation function will be different. Okay, so let's do the gating right now. Okay, so the gating should be done by your context S. Okay, because now we are quite sure that this is the context. We don't have to do a concatenation because the S can then control just the gate itself. So let's not do this concatenate. Okay, instead what we'll do is this. We'll just do a sigmoid. Okay, and then this sigmoid will be will take in input 2, and then it will give the sigmoid here before we do a multiplication. So we do like this. So the input signal, okay, the input signal, input 2 here, it will gate our flow of information through the network. So this is the gated version of what we are trying to do, and let us try to implement this here. So we gate this dense network as well, so we can do this. Why not we just call it gates? Okay. And the gate just purely depends on the input 2 here. Okay, let's just see whether this sort of works. So we do a gate. This is not a self-gating because the gate will be determined by the uh basically the gate will be determined by the input parameter. So from there we can form the gates needed for this. So we do a multiply. So just to check the Keras multiply function. So the multiply layer is a layer that multiplies element wise, which is great. We can use this element wise to do the sigmoid. Okay, because we have a sigmoid here, then we multiply by the original x. So let's try this. Okay, and then we see whether this kind of works. So we are using the context now as a gate to determine what signal flows through. So yeah, I'm not sure whether this will work, but it's worth a shot. It's worth a shot. We can try it. So I think just gating may not be just gating alone may not be enough. Okay, may not be enough. It looks like it's still not doing very well. Okay, but this last one is kind of learning the gate. This last one here is learning the gate. This two here is still not exactly that great, I would say, but at least there's some improvement. Okay, let's see the validation. It's about 5%, 3%, 4%. Yeah, but one thing for sure is the last one is working. It's actually improving. Actually, I wonder if maybe we just need more time for it to learn. Okay, so just to make sure that the gate thing is working, let's maybe scale it back down to 2, because just now we were sure that this kind of worked for the earlier model without the gate. So we just do for 2. So instead of doing a gated value, maybe sorry, not instead of doing for all 26 possible code words that we can generate like through this function here, instead of doing s for all 26 values, we do s for 0 and 1 only, which kind of worked for the earlier ResNet like model with 10 layers or 11 layers. I think we can try to see whether it can decode it. Yeah, look at this. Okay, so it worked for the earlier one. So can the gated version of this model solve this problem as well? So that can basically, so instead of like earlier on, I just concatenated the two inputs with the input signal here. Now what I'm doing is I'm just doing a gate with this input 2 to all the MLP layers, all the dense layers. So I gate, then I multiply. Yeah. So actually, I'm thinking maybe I still need to put in the signal here as a concatenate, because there are some cases whereby you actually need to do a minus s over here. So the s parameter is actually important in the calculation. So maybe in other than just having the gate here, the input 2 maybe should still be concatenated here. But let's try. Okay, we see how this model is. It's not too bad. It's about 20. So this plus 2 is working. Okay, let's try the theory that I was thinking about. Let's just do this. And uncomment the concatenate layer, and we see whether it learns better. So now we do have the input being factored in, okay, and we still use the input 2 to gate it. Okay, somehow it doesn't work as well as it did before. Before, when the input 2 was the only one to do the gating and it didn't come into the original signal itself, it kind of worked better if we were to do this. After I concatenated this, doesn't seem to work that well anymore for some reason. Not too sure why, but let's see how this is. Okay, so for this, it's working well, but for the first and the third character, it doesn't work too well. Hello, how do I pronounce your name? Sir Dice a lot. Yeah, I'm just doing a fun experiment that I thought of myself to see whether the neural network can like decode a certain complicated equation. It's like ciphertext that uses a function to generate the text. So you see the four characters are generated with like certain permutations or certain functions of the first original four characters. So it looks like the first and the third didn't work well. So this is the function that I'm using. Like the function is here. So based on the position, like position one and position two, so we actually do four different functions. Yep, four different functions here uh, that challenges the current neural network design. Yeah, because current neural network design only does addition of the input weights and the inputs. I'm not sure if you're familiar with how the neural network works, but it's just a summation of the weighted sum of your inputs plus a bias term. Yeah, which means that stuff like this will be very challenging. So yeah, let's see whether it can work out. Okay, so it kind of didn't work out. Kind of. Oh, that's good. That's good. Yeah. So now I'm doing some form of a gated ReLU, some gated activation function where I gate the sigmoid to the output of the like the node. So previously without the gates, it was working quite well, but now after the gate, it kind of went downhill. So let's remove the gate. Okay, let's just remove the gate here. Let's just go back to the original one with a ResNet like architecture where we go through this. Let's remove the gate now, and then we see that the network can learn. So yeah, oh, I'm just using only two shifts right now. Where is it? Here. My shift value is only 0 to 1. Yeah, only two. Let's see whether it can learn that function. Oh, very nice. Yeah. So your computer vision pipeline, I suppose, uses CNN kind of architecture. Yeah. So CNN works well for the current neural network kind of structures because typically for features, you just need to sum them up, then see that they pass a certain threshold, and then you can detect whether or not it's a feature. Yeah. So neural networks, the main use case is mainly for images right now, images, and also like word processing, because word processing itself has a unique structure whereby you can actually encode the words into like embedding spaces, like vector spaces, and then you can then do vector addition. Attention-based models modify that vector, but it's still a vector addition. So anything that involves addition, neural networks do pretty well. But the problem that I set for it It's a problem that doesn't just use addition. It has like multiplication and modulo, which because I've done some experiments on modulo before last time. Yeah, it's kind of hard. Yeah, for your project, if you are doing cleanest edge image in adversarial condition, right? Yeah, I guess you could do some form of maybe contrastive learning. I mean, if you have heard of it before, it could help to make it learn better. You could like put two similar images together and then just say this is correct. You put one similar and one graffiti one, then you say this is not correct. So it can potentially it's something like adversarial method to learn where you give it counter examples and say that this is not the same, this is the same. Yeah, it might help. Yeah. Yeah. I mean, I guess you can also just do as a classification based problem. That should be good enough. Okay. What happened to my model here? I mean, it was yes. You see, it's going up. It's going up. Okay, so the gate actually kind of hurts problem. Uh, Nice. Hope to see good results for your thesis, I guess. I'm currently a PhD student. Yeah, and my research focus back then was on network pruning. Now is on network generalizability, and I feel like there's a lot of things that have not been discovered yet on the neural network generalization properties, which is actually inherent to the structure of the neuron that we use right now. Yeah, so I'm thinking actually the structure of the neuron right now, while quite versatile, it is uh, it is not the best. Yeah, it cannot model a lot of functions that easily. Yeah, yeah, I do understand that. I mean, I was a bachelor student once. Yeah, good luck for your thesis. It will take a while to write, but I'm sure you can write it. Okay, so anyway, back to the topic here. Uh, if I take away the gate, you see, it was working. Okay, but if I add in the gate here, the activation function somehow seems to hurt the performance. Yeah, like this one and this one cannot go up. So without the gate, it could sort of learn, but yeah, I'm just seeing whether or not this kind of gated method okay. Yeah, looks like it's not not exactly helping the model right now. I mean, you can look at the accuracies here. This is the first character's accuracy, second character accuracy, third, and the fourth. The fourth one is easy because the fourth one, the function used was this. The function used was this x0 times s, which means that there's only like you can actually memorize the mapping. Like you can hardcode the mapping if you know your s. You can hardcode the mapping already. So this is easy. But the first few are difficult. These are difficult. Yeah. So x0 means like position one character, x1 is position two, x3 is position three. No, x0 is position one, x1 is position two, x2 is position three, and x3 is position four. So yeah, basically based on the four initial input characters, apply some form of mapping, and then you get back your four output characters. So right now the last character, the function is quite easy. It's accuracy one. This one is 2922. I wonder if it can improve actually. Let's try running again. Yeah. So actually, oh, the age detector you're using implements linear prediction. Hmm. But why do you use an age detection though? I mean, you are doing graffiti science, right? So, um, I mean, you could do just like by image examples, right? Then just like the classifier learn. or are you doing a feature engineering, hand design features? Mhm. Oh, look at this. The accuracy is increasing. So actually the gated version actually can learn also. Look at that. Based on the gate of input 2, it's learning pretty well. Oh, that's not bad actually. That's not bad. Okay, let's run again to see whether it can really work. Yeah. So actually for neural networks, you realize if you want to train end to end, you need a lot of data because you need to fine tune the individual sections of the network properly in the right way. Which if you have very few data, it can be difficult. So a lot of practical applications that you want to do, like especially for imaging, you try to find a large model that has been trained on a large data set that is very similar to what your use case is. So maybe for yours, if you are doing a graffiti road sign thing, maybe you want to get a data set that does on road design, or a data set that uses roads, like housing data set. I'm not too sure whether ImageNet is also okay because ImageNet does have a lot of road signs as well. So if ImageNet is okay, you can do transfer learning from a trained model, like a trained CNN, like a ResNet, trained ResNet on ImageNet. Yeah, in my experience, using a pre-trained model works really good if you have very little data because it has already learned the right features, and then you just need to use a final linear layer to like classify the features. Okay, so anyway, back to the notebook. I'm actually quite impressed. Okay, the gated ReLU functions actually are approximating to one. I mean, it does look like it's learning. Okay, let's try again. Let's try again. I mean, it does look like it's going. Okay, so it's not learning fully. Okay, uh, there's some there's some loss. Okay, unlike if when I didn't use the gate, when I didn't use the gated function here, when I didn't do the gate, there was no. I mean, I could reach almost like 100% for all the characters, but now there's some loss. So you see, like over here, my training accuracy is about 97%, but the validation accuracy is maybe about 64%. You know, sorry, that's a loss. What's the validation accuracy is here about 80%. So for the first character, is having a hard time predicting the first character. Where is it? Where is it? Where is it? Where is it? Here. Yeah, I think if you use if you use a transferred learning model, you will actually have easier time because a lot of the features can be shared to your model. Transfer learning, I think, is the way to go in the future or even now, especially when you don't have so many compute resources. You just take on what other people have done that is similar. Well, actually, this is not bad. You see, it's 86%. We can try it. AMCD, and you see shift value like that. It's pretty cool. It's pretty cool. This one is working. Yeah, it looks like it's working. So let's try to use this gated model. Okay, so if the gated model can work, then there's no need to do what actually I wanted to do. Let's try with all 26 values and see whether okay the gated model can actually like help us to get the right output. Okay, good luck model. Yeah, I'm counting on you. That's very nice actually. If you started learning machine learning about a year ago and you can do your CNN already, that's good. Yeah, I mean there's a lot of things in deep learning that are currently still quite arbitrary. People haven't found the right secret sauce or the right mathematical formula to do things. So it's can be quite hand wavy. So as of now, just using established architectures, especially for you who have just started. Using established architectures would be helpful because it's tried and tested. Like CNNs, you can just use like a tried and tested ResNet. Yeah, so ResNets are typically better. Uh, I mean, I've used the nets before. ResNet is very competitive. Without the skip connection, your network doesn't perform as well. Yeah. So ResNets, I just type here for you just in case you want to find. Yeah. So where I did my dense layers here, I also did a ResNet style. I take the previous layer, I do some form of blocks here, and then basically I add back my previous layer here. So it's a skip connection. So one part of the network goes through this block, and another part gets added. Yeah, cool, right? You see, TensorFlow, you can do stuff like this. You can do a for loop like this. And you don't have to specify the blocks like 10 times, which I think is very cool. In the past, in TensorFlow V1, you cannot do Pythonic style statements like this, but they have changed since then, and I'm glad they changed because now you can do stuff